My name is Marianne, and I'm the current director of the Center for Climate Science and Engineering. I'm delighted to welcome all of you to our very first symposium. I will take a few minutes to welcome all of you and introduce our center, and we are going to have a few research presentations followed by reflections by climate scientists on the interdisciplinary research. And then in the last half hour, we would like to open the floor for discussion, and I hope we will have a lovely exchange of opinions. So the Center for Climate Science and Engineering is a research and education center within the University of Toronto Civil and Mineral Engineering Department. It was established in 2019 through the funding from Dean's strategic funds. And we have a multidisciplinary team of faculty members in our core group, and I'll introduce them in the next slide. The research areas include climate science, transportation, structural engineering, building science, and life cycle analysis, all connected together with the changing climate. The core executive CSE team has faculty members from different departments. From civil and mineral engineering, we have myself from structures group, Marianne Hatzopoulou from transportation, Daniel Posen, Lifecycle assessment, Marianne Touchie, building sciences. We have Graham Norwell from chemical engineering. For climate science, we have Paul Kushner, Department of Physics, and Karen Smith, Department of Physical and Environmental Sciences from UT Scarborough. We also have Dr. Jamie Fine, who is doing an amazing job in coordinating our day-to-day activities as the CSE manager. So we have research objectives to look into climate change mitigation and adaptation strategies, improved carbon accounting, and GHG reduction efforts. We also have educational and outreach activities to educate engineers and scientists on how climate change impacts engineering decisions. We are going to provide a few sample research presentations. That's why I'm not going to go into the details. What I want to emphasize here is that one of the big challenges translating global climate change knowledge into actionable knowledge that practitioners can use in local scale. We need to do the research in adaptation or mitigation on a variety of scales. And at CSE, our team focuses on different scales, including building, neighborhood, regional, and global scales to study different aspects: building science, structures, transportation, energy. And we are going to have a few presentations that summarize our research efforts on this front. And for the education and outreach activities, CSE offers lecture series, workshop series. Recently, we received funding from eLearning Ontario, and in collaboration with Western University, we are developing 8 online modules which will be made available freely through eCampus Ontario. This will be a short duration learning opportunity for senior undergraduate and graduate engineering and climate science students. We also developed two graduate courses, one of which is currently being offered, and the other one will be offered in the winter semester. Last summer, we offered a deep course for high school students focusing on engineering solutions in the face of climate change. And with that, I can transition to the first research presentation, where I co-lead with Professor Kushner from Department of Physics. Here, we are developing a computational wind engineering framework to study the climate change impact on high-rise buildings in dense urban environments. And in our group, we have postdoctoral researchers as well as graduate students that are listed here. And in the earlier part of this research, we collaborated with Environment and Climate Change Canada and NCK, an engineering firm in Toronto. So why is the wind load important? We can think of it from 2 aspects. As engineers, we need to design structures with different requirements in mind. The first one is the safety. So we need to design in a structure that we need to design in such a way that it doesn't fail or collapse. The Tacoma suspension bridge collapse in '94 is an example of a structure that failed under wind loading. And in addition to safety considerations, we also make sure that the serviceability limit states are satisfied, which means that the drifts, accelerations, and vibrations of the structure are kept under some limits so that the occupants can use that structure as designed. We wouldn't want the structure to experience non-structural component damage. For example, the picture on the right here shows the damage to the facade of a building during a typhoon in Hong Kong. And we also wouldn't want the structure to experience large accelerations and vibrations, making the occupants experience motion sickness or seasick. So to make sure that we design the structures properly, we use what is called Davenport wind load chain, developed in 1960s. And in this load chain, on the left side, we start with the wind climate. And typically, in traditional application of the wind load chain, this information about the wind speed and wind climate comes from historical wind measurements, typically from airports. And now we need to introduce the influence of the terrain. If we are designing a structure in open terrain with a smooth surface, the wind loads or the wind speeds near the surface are going to be much larger than designing a structure within a rough terrain, such as a city center. So depending on where the structure is going to be built, we need to adjust the wind speed profile accordingly. We then need to consider the aerodynamic effects, which is simply the interaction between the wind flow and the structure that is causing the loads acting on the structure as the resultant of the wind pressures. Depending on the complexity of the structure, if we are allowed to use codes and standards, we can quantify the wind loads using the codes. In Canada, we are using National Building Code of Canada. If we are only interested in the along wind direction, we can use some stochastic wind load methods to quantify the wind loads. If we are interested in understanding the three-dimensional wind load acting on the structure, and if we have capability to do experiments, we can use wind tunnel testing, or we can do a virtual wind tunnel using computational fluid dynamics. Within our group, this is the fourth one. The D is what we are doing. Here we have a structure in a virtual wind tunnel, and we can visualize the wind flow around the building at different angle of attacks. And once we quantify the wind load, the next link in the chain is the dynamic effects. And to be able to do that, we need to simulate our structure using structure dynamic tools. And finally, once we finish all the steps in this link, we can have quantities of interest at hand, such as drifts, accelerations, velocities of each floor. And then we can introduce our collapse prevention and serviceability states to decide whether or not this structure performed acceptably. So when we started doing our transdisciplinary research, what we have done is we took this chain and we left the second, third, fourth, and fifth link as it is. What we have done is that instead of using the historic data for the first link, we obtained that information from global climate model projections. Here we have the graph starting from 1980s until the end of the century from 19 global climate models for yearly maximum wind speed data. And we there are different techniques available. In this particular case, we performed statistical downscaling, and Karen Smith and Paul Kushner might talk about this a bit more in detail at later presentations. And once we have the bias corrected downscale data, we can use extreme value theorem to estimate future design wind speeds, and we can propagate that information through this chain so that we can understand what happens to a selected structure under changing wind climate conditions due to climate change. The last slide that I want to discuss very quickly is this chart provided by Chester et al. In 2020 to keep infrastructure reliable under climate uncertainty, and to classify the structures into these domains. On the horizontal axis, we have the climate change. To the right, the climate change variable, it can be temperature, snow, wind, or precipitation. To the right, the climate change in the future condition is going to generate more severe conditions. To the left, due to climate change, the conditions are going to be less severe. On the vertical axis, we are comparing the past or current conditions with the design conditions. So upwards, we have the past conditions less severe than the design. So the structures so far have performed as well as they have been designed for, because the design loads were exceeding the actual loads that the structure experienced. Downwards, the past conditions were more severe than design. So in this region, we may have already observed some failures because the conditions exceeded the design loads. And when we did this study for selected building in downtown Toronto, under different projected wind scenarios, for some of the cases which we called future loss scenario, we found that that particular downtown Toronto building was in this guarded domain. So the infrastructure, that structure in the past, experienced loads that were lower than the design loads specified by the code. And in the future, the design wind speeds are going to get less. So the structure falls into this domain, guard domain. But the same structure under different projected wind scenarios fell into the elevated domain, which meant that it in the past the loads were lower than the design loads, but in the future, in some cases, the wind loads may be increasing, which requires us to come up and study some design changes or supplemental device introduction to the design and some measures to adapt to this change. So with this, I would like to invite the next speaker. And if there are any questions, I would be happy to answer either if you have time right now or at the end in our 30-minute discussion period.
I don't see any questions at the moment. I think it's safe to say we can keep moving on, and I think it's Marianne Touchie. So.
Okay, great. Thanks, Jamie. Thanks, Oya, for that great summary. Let me just get my slides up here. Sorry, I'll just share my screen. There we are. Can everyone see that? Oh, I can't see you guys anymore. There you are. Okay, great. Wonderful. Well, hi, everyone. My name is Marianne Touchie. I'm an assistant professor jointly appointed in civil and mineral engineering and mechanical and industrial engineering. And I've been pleased to be part of the CSE collaboration for the last couple of years. So I'm going to share with you some work that was done by a former master's student, Joey Liu, on the impacts of climate change here on campus, actually. And I also want to acknowledge some visuals that I've borrowed from Mark Couture here at U of T and Cameron Thompson from Arup, who did some extensive evaluation of how our campus needs to change the way it operates in order to both mitigate and adapt to our changing climate. So we'll start off just with a bit of context. Sorry, I'm not sure where my slides are not advancing. Is that working? No. There we go. Oh, there we are. So just a bit of context to sort of put U of T in sort of the larger realm of GHG emitters in Ontario. So we are the third largest emitter, the largest university emitter in Ontario. So we're a big emitter, but we're also growing, and we're going to grow quite a bit in the coming decades. And along with that, as we all know, we're also facing a rapidly changing climate. So with that, with increased temperatures, we will see a decrease in our heating loads, but also an increase in our cooling loads. And I'm focusing here on heating and cooling because the work that we do is really looking at how building performance is impacted by climate change and in turn impacts climate change, because space conditioning is responsible for the vast majority of building GHG emissions, and so something that we need to pay a lot of attention to in the coming decades. So this growth on campus paired with this changing climate means that we're going to see fairly significant changes to our peak load projections for both heating and cooling. Particularly cooling is going to become a major problem for us in the coming decades. And then of course our annual energy consumption is also going to increase, primarily driven by that growth on campus. And it's not just, I mean, of course, all of this is about ensuring that we're reducing the effects of climate change. We also need to consider on campus the cost of these changes. And so as we move to a low carbon economy, there will be either through carbon pricing or changes to our fuel sources, significant impacts on the university's operating cost. So for all of these reasons, U of T has really undertaken a fairly aggressive carbon reduction strategy, fairly aggressive approach to carbon reduction in the coming decades. And ideally by 2050, the goal is to get to the point where our carbon emissions are reduced on the order of 80% from where they are currently. And then those are offset by renewables, either on or off campus. And so this path over the coming decades is influenced by a number of different components, contributing components. So how our new building design standards change, how we provide energy on campus. But what we're going to focus on is this little tiny green slice here. So we have hundreds of existing buildings. And I realize it's kind of a small slice of the pie here when we're looking at our energy contribution, but we also need to think about the fact that buildings are for people, and we need to ensure that these people are kept healthy and comfortable and happy in these buildings as we move forward in our changing climate. So thinking about this from an adaptation perspective and ensuring that our buildings, our existing building systems are designed to keep our occupants comfortable and healthy in a changing climate. So with this, looking at these existing buildings, we really need to think about this from two lenses. So I've already mentioned the impact that climate change is going to have on building design and operation. So we need to adapt those buildings to deal with those changing climates. But while we're doing so, we also need to ensure that we are reducing our energy consumption and the subsequent GHG emissions for that that mitigation piece as well. So making sure that we're addressing both of those. And although there are some synergistic retrofits, there are different things that we need to focus on for both the mitigation and adaptation side of things. So to reduce our GHG emissions, we obviously need to be significantly reducing our energy consumption and ideally shifting that energy consumption away from GHG emission intensive sources. So that means transitioning away from natural gas and electrifying. And then to adapt to this changing climate, we're going to need to see significant increases in our capacity to provide cooling. A lot of our buildings on campus don't have central cooling, so that's something that we're going to need to consider. Also increase backup power. So as we see increasing frequency and severity of extreme weather events, our aging infrastructure on top of that, we are likely to see increased power outages. And so making sure that that's built into our retrofit strategies as well. And then also there are a number of things, but the other thing I just wanted to highlight was also a robust ventilation strategy. And this has to do specifically with outdoor air quality events. As you know, we've seen out west, but also we saw this summer in Toronto. We need to ensure that that our buildings are designed to meet those requirements as well. So this is really the lens with which Joey approached his study. And so the original scope of this study was meant to actually take a selection of buildings from across campus representing different archetypes. So from fairly modern buildings with centrally controlled systems through to our historic buildings with relatively decentralized systems. The realities of gathering the information required to do this study prevented us from doing the suite of buildings, but this was the building that became the focus of Joey's work, which is a couple of decades old, a relatively small, simple building on campus, the Fields Institute. And the way that we go about analyzing a building is basically constructing a virtual model of that building and looking at all of the heat, moisture, and air transfer that happens within that building, and looking at the energy, first of all, the energy inputs, so the natural gas and the electricity required to heat and cool and ventilate that building and provide lighting and plug loads to all of the occupants. And then we control the building essentially, or we control this model to essentially mimic the conditions that one would see in this occupied building. So we're tuning the temperatures and the indoor temperatures and the amount of outdoor air that's delivered to these various spaces. And so once this model is built, we then calibrate the model to ensure that the modeled energy outputs match the existing utility bills for this building. So once we have a calibrated model, then we can start to play around with things in this virtual space. So we want to, the objective is really to model how this building would respond to a changing climate. So the way that one of the inputs to an energy model is what we call a weather file, which is essentially a snapshot of a year, usually a typical meteorological year. And so you would run that model and get the output energy consumption. But what we did with this building was actually instead of running it with our current weather file, we replaced that with a future weather file that was estimating what the conditions might look like in the 2040s and what the subsequent energy outputs would be. And then what Joey did was develop a series of both passive and active retrofit strategies to see if we can actually reduce that energy consumption. So he tried a number of different things, including optimizing solar gains through things like overhangs and fins. You can see these purple things over here on the left on the retrofitted building. Window films to, again, try to control solar shading. Retrofitting wall systems through increased thermal insulation, actually replacing the windows with high performance units, doing air sealing, so sealing up any uncontrolled air leakage across essentially holes in the building envelope, which would let uncontrolled air leakage pass through, which impacts your energy consumption. And then the one active measure that was installed was recovering waste heat from our exhausted air and delivering that to our incoming air. So trying to recover some of that waste energy in order to reduce our energy consumption. So, so this slide just sort of summarizes all of his modeling results. And there's a lot going on here, so I'm not going to go through everything in detail, but I'll just point out a couple of things. So first of all, the red line is essentially where we want to get to by 2030 in order to stay on track with the university goals of GHG emission reductions. So the column over here on the left is our basically running that virtual building under current weather conditions. And then the next one is simply what happens when we run that with a future weather file. So as I described, we're seeing reduced heating load. So that's why that energy use is actually coming down, because that reduction in heating load is actually more than offsetting our increase in cooling load. So that's a good thing from a GHG emission perspective, but we're still above our goal, our 2030 goal, and way above our 2050 goal. So we have more work to do. So these next bars in the middle here are all representing our passive retrofit strategies. And you can see that they're all making sort of very small incremental gains here. The single most effective retrofit strategy was that energy recovery that I spoke about. But really it took combining all of the passive and the active measures to just get ourselves below that 2030 target. So this is an incredibly significant, very costly retrofit measure. When you're doing things like replacing windows and adding insulation and doing a comprehensive air sealing job and adding energy recovery to the mechanical system. So this is fairly significant. So I show this not as a bad news story, and that's not intended to be that, but just to underscore the amount of effort that goes into improving our existing buildings and why we can't ignore that little tiny slice of our existing buildings that we see here. So there is a lot of work to do on campus, and a lot more screening and prioritizing that we need to do. But we also need to acknowledge that all of our new buildings need to be incredibly high performance, and we need to be fundamentally changing the way that we deliver energy on campus. I realize I'm a little bit over time here, so I'm just going to skip ahead really quickly just wanted to give a plug for our current CSE work. We have another master's student who's now exploring in situ retrofit strategies for what you probably see all around us downtown, these beautiful, I say beautiful kind of sarcastically, curtain or window wall systems, which are notoriously poor performing and I think present a huge risk to residents, but also climate risk if we don't significantly improve the performance of these systems moving forward. So we've got a student who's working on that right now, which is really exciting. And then the other project, which is not CSE related, but I just wanted to mention briefly, is moving beyond sort of climate positive and actually incorporating people into the mix here. So with some of my social science colleagues, we're working on net positivity, both for people and the environment on campus. So that's another exciting project that's coming down the pipeline. Anyway, sorry, Jamie, I went a couple minutes over, but happy to answer questions now if there's time, or we can switch to the next presenter.
There are some questions here. Should we do that now? Is there any? I think we should just, if you want, Marianne, if you look in the Q&A tab, maybe type in the answer there.
Sorry, where is the Q&A tab? Oh, there. Oh.
Yeah, down there. There's some questions down there.
Yeah, I'll answer these while the next speaker goes, and then we can. Yeah. Okay.
Just
sure,
to keep on that.
Definitely.
That track to make sure people, only booked a little bit of time to give time for those to see the presentation. So I think next is Daniel. Yeah, Daniel.
Okay, are you seeing my slides and are you hearing me? I see nodding. Excellent, thank you. So hi everyone, I'm Daniel Posen. I'm also in the Department of Civil and Mineral Engineering. And I'm going to be talking today about a number of different pieces of work, all sort of related to this idea of what I call flipping the question and looking at the implications of climate change for greenhouse gas mitigation. And I'll explain in a couple slides what I mean and why I see that as flipping the question. I'll start with just a little bit of broader background about who I am. So I work in a very interdisciplinary way, really thinking about providing quantitative decision support for environmental decision-making. And it involves a mix of a bit of science and engineering, economics and policy, and broadly what I would call systems thinking, right? So really trying to think through multi-systems implications. I have a sort of unusual academic background with degrees in chemistry, economics, and engineering and public policy. So it sort of works. And the kind of tools that we use broadly are things like lifecycle assessment, where we try to think through the environmental impacts of a product or process from cradle to grave or cradle to cradle, however you want to put it. Tying that in with economic modeling of how new products are going to shift demand in the market and what implications that might have for environmental impacts. And then broadly tying it together with decision support and uncertainty modeling and thinking about how do we make decisions and how do we support sustainable decisions under conditions of fairly deep uncertainty in these spaces. And so as a result, because I come at this more from the tools and the principles of trying to tie together systems, we apply these ideas of life cycle thinking, again, thinking through systems, to a wide range of different systems and technologies. So I've been doing a lot of work with vehicle technologies and thinking about fleet scale, life cycle assessment and policy modeling. How do we decarbonize our transportation fleet? I've been doing a fair bit with the electricity system, and there's an interaction there, of course, with electric vehicles that I'll be talking about a bit today, and uncertainty and variability and how we model those emissions. And more broadly, thinking about renewable fuels and chemicals and what our energy systems look like going forward. Okay, so that's just sort of the deeper background on where I'm coming from and why you're going to see a number of different angles in today's talk. Broadly, the role I see for myself within the Center for Climate Science and Engineering, it's bringing together this life cycle look at the mitigation, the greenhouse gas reduction and mitigation piece, but it's also looking for these new interactions between climate models and engineering systems. So what I have here is this mental model, at least that I had going into this, of what these interactions look like, that we have mitigation, actions that are going to reduce emissions that cause climate change, and that lets us explore what our emission pathways look like. And then we tend to take those emission pathways and we're going to feed them through a climate model, right? To understand what impact these different emission profiles, these global emission profiles will have on the future climate. And then that tends to feed back to, well, here's what the climate's doing. How do we adapt? How do we get ready for this changing climate? And a big piece of what I want to do within this center is to add this additional arrow, to think, well, not only do we need to think about how that changing climate is going to impact our ability to manage it and our ability to adapt, and what do we need to do to respond to the changing climate, but at this point, some degree of climate change is already locked in, right? It's sort of too late to say we're going to avoid climate change altogether. So how does the existing warming that's already happening affect our efforts to reduce emissions? And so this is sort of what I mean by flipping the question. Instead of asking, what do our emissions do to the climate? What does climate do to our emissions? And so I'll talk about a number of things that we've been looking at within that. So today's presentation, I've got a number of projects that fly the CSE banner. I'm going to try and talk through a few of them. I won't get through all of them, but I just want to give a big thanks to the students and postdocs who've been working on this. So Shui Song, Daniel, Elise, and Sherry have all been directly affiliated with the Center for Climate Science and Engineering. And we've got some ongoing work that's just starting now that won't be featured today. So we'll leave that there. I think we'll probably be sharing slides later if you want to see who did what, but just know that most of the work I'm presenting today was done by someone else in the group that I just happened to lead or happened to help supervise. All right, so where does this work start? So a lot of the work that we've been doing is going to be anchored by these new runs that we've made of a variable resolution climate model. So specifically looking at a representative concentration pathway, 8.5 watt per square meter. So basically one of the more severe potential climate change pathways. And we're focused in particular on what this means for the climate in 2040. Realistically, whichever pathway you take, there's a fair bit of warming by 2040. So we're taking the most severe scenario as a bounding case for what the climate might look like in 20 years. But even if you take a more moderate case, you don't tend to get dramatically different results. All right, now there's lots of acronyms on this slide. So basically, this is just for anyone in the group who's coming from this climate science domain. Realistically, if you want to know the details about the climate model we've run, Paul can talk about that in a couple talks from now, right? That's why we're collaborating. I'm not the climate scientist in the group, but what I'm showing you here is on the left, we have this variable resolution run where we're really zooming in to high resolution over Southern Ontario over here. I switched that to a laser pointer. Okay. High resolution over Southern Ontario, but effectively we're getting pretty good resolution over the entire North American domain, which you're going to see about. All right, so we take all this work that goes into building out the climate model, and then we're looking at translating these climate models into metrics that are relevant, in my case right now so far, to vehicles and electricity systems. And some of these metrics that we care about are going to be things like fuel cold weather properties. So in particular, biodiesel, it's a renewable alternative to conventional diesel fuels. And one of its challenges is it doesn't have very good cold weather properties, that at relatively moderate temperatures, it starts to precipitate out, basically turns into a wax and stops being able to flow properly. Basically, you can't run a full biodiesel in the middle of winter, not without some kind of chemical correction so that it'll work in our existing trucks, right? So this really matters. So to be able to look at this and how much of these fuels we can use, what you really need to understand is what is the coldest weather we're going to face. And as the climate warms, we can potentially start using more of these renewable fuels because they don't face as severe winter limitations. We're going to be looking at vehicle energy use. And we did some work looking at what are all of the different climate parameters that might impact vehicle energy use, and zoomed in on, in particular, on ambient temperature, which has a fairly substantial impact. So I don't think anyone is surprised to hear from that last talk that yes, temperature is going to affect building energy use because we use a lot for heating and cooling. Turns out temperature can also have a fairly substantial impact on the energy used by our vehicles. And in particular, electric vehicles, which is where we're heading, are particularly sensitive to the temperature. And then we can translate that not just to the total energy use, but what are the implications of electric vehicles on peak demand? So one of the things we really care about in electricity systems is it's not just about the total energy we use, it's also about that match between supply and demand. And so there's a question around when are electric vehicles going to charge, and how much more might they need to charge during extreme weather days, and what's that going to do to the peak demand, the hour with the highest demand on our electric grid and our ability to meet that demand. And then separately, and we haven't merged these two topics yet, but that's an area of ongoing work. Separately, we looked at, even in a world without electric vehicles, what's going to be happening in that electric grid, and what's going to be happening both to supply and demand of electricity as the temperature changes going into the future. All right, so these are some of the domains that we've been investigating. So here's that chart from before. So metrics relevant to mitigation and to engineering systems, in particular, like I said, vehicle and electricity. So what do we need to know? We're going to need to know things like, what is the 2.5 percentile minimum temperature? Because that's how the fuel regulators tend to deal with operability of these fuels that don't work well in the cold. They look over the last 30 years at any given 2-week period. What's the 2.5 percentile coldest temperature, right? So they don't take the absolute coldest, right? At a certain point, you can't bound to maximum minimum temperatures, but they say, hey, let's take a threshold at 2.5 percentile. That's the cold temperature for which we need to design our fuel systems. How is that changing over time? We get daily temperature profiles for passenger vehicle energy use. And then we're going to take daily and seasonal, both temperature and precipitation profiles for power generation and demand. And precipitation is going to matter in this case because we have a lot of hydropower in Ontario. We'll talk a little bit more about why temperature matters. All right, so that's the sort of the big picture of what we're doing. I'm not going to get into details on the methods, but what I'll do is I'll run you through a number of the results we've been coming up with. So one, climate change increases biodiesel operability windows by up to several weeks. So what I'm showing here are maps of 3 different fuels with 3 different cloud point types. So there's a lot of detail that I'm glossing over here and maybe oversimplifying, but fundamentally, the top panels are going to represent summer fuels, the bottom panels are going to represent winter fuels, and the middle panel sort of an in-between. On the left, we're showing for each state or each province within our grid, what is the maximum number of weeks of the year that region could use each one of these fuels, right? So for our winter fuels, we'll notice in the southern states, they're all in yellow, pretty much winter fuels they could use all year. There's no problem with these fuels. All right, whereas our summer fuels, we do have some fairly substantial limitations. You only can use these for about half the year at best in many of these jurisdictions. So this is under the historical climate model. And on the right, what we looked at was under climate change by 2040, under this relatively severe climate change scenario, how many more weeks of biodiesel use do we get if we're looking for the longest stretch that we can use each of these fuels? And again, there's a lot of subtlety here, but the answer is actually, yeah, there are some meaningful changes in terms of how long we get using these renewable fuels or any other fuels with poor winter properties. And yep, as the climate warms, we get to use quite a bit more of this, and that can have some meaningful implications for how we decarbonize our transportation system. We looked as well at, even without the changing climate, is there a way that we can redistribute what we call these supply orbits? So these orbits, basically, we group together geographic clusters that are used for distributing the fuel. And that tends to be the limitation. You have to look at the coldest point within that cluster, within that supply zone. And that is what limits which fuels you can use. And so we did some work looking at, well, could we recluster these zones? So instead of using the current existing supply orbits, what work can we do clustering along similar temperatures to reduce what we call the cloud point giveaway. So to reduce the amount at which we're over designing our fuel. And we did find some different zones from the current zones. And we did some work looking at, what if you were to start drawing boundaries around individual cities, for example? So instead of saying, because Toronto is in zone number 1 or whatever zone it is, it has to meet the coldest temperature throughout that zone. What if we drew a boundary just around Toronto? And the answer is, again, you get fairly different results, and you get the ability to incorporate quite a bit more renewable fuel when you start to tailor and narrow those zones and are not limited by the broader supply constraints of larger temperature zones. All right, then we move on to electric vehicles. And so it's fairly well known that electric vehicles have a strong temperature sensitivity. There have been a number of studies that have done this empirically, just tracking electric vehicles over the course of the year. And they tend to find that, you know, in the middle of winter, electric vehicles are using 50, 60% more energy than they would in mild weather. And so we did some work looking through the literature and trying to understand the breakdown. Why is this happening? There's definitely a reduction in battery capacity that's happening in cold weather. But fundamentally, a lot of it is just down to exactly what it is with buildings, heating and cooling of the vehicle cabin. So there are some other effects, but main message here is it is actually driven by just temperature control within the vehicle cabin. And so what does that look like going forward? What does that look like going forward under scenarios of climate change? So on the left here, we're showing percentage energy change that can be expected by 2040 relative today for combustion vehicles, for conventional gasoline-powered vehicles. On the right for electric vehicles. And what you tend to get, maybe not surprising, is you get offsetting effects, right? So in the winter, the winters get warmer, get more mild, and we use less energy in the winter. The summers get hotter, a little more severe, we use more energy in the summer. And that does tend to offset. So we end up with relatively small changes overall for the course of the year, about plus or minus 1%, depending on where you are for combustion vehicles, but plus or minus 2 to 3% for electric vehicles. And what I would say is, although these numbers look relatively small, we have to remember that a 1% increase, say in gasoline use, that's 500 million liters of gasoline across the US, right? We're still talking very substantial volumes of fuel because we're talking throughout the entire transportation fuel use, which is a huge contributor to our greenhouse gas emissions. But then when we start to think about the fact that these things come about from offsetting summer and winter changes, we have to start to wonder, well, when might it matter that on a given day, on a given very cold day or a given very hot day, we're using a lot more energy? And the answer is, that's where we get to this question around electric vehicles and their impact on the grid. And a lot of studies that investigate electric vehicles and how they might change the load profile for electricity systems or the energy they might use tend to ignore the temperature effect, right? They tend to say, we're going to use an average fuel economy, an average fuel consumption for these vehicles throughout the year. And so then we took a look at, well, how does this change if we start to incorporate, if we push a little harder on saying, no, whenever you're going to do an analysis of electric vehicles, you've really got to think about that seasonality. And what we're showing here in yellow are the change in energy use for the average monthly temperature profiles. So even just for an average January, our electric vehicles are using 50% more energy. Well, that really matters. And then in blue, we're looking at the extreme days, the hottest or coldest day. So on the single coldest day in January, we're talking up to 80% more energy use for electric vehicles. And then we think about how that again impacts the charging and our ability to meet that demand peak, depending on when people are charging. And so then we go into these scenarios we built a number of different scenarios around, well, when are people going to charge? Do they charge as soon as they get home? Do they charge when they get to work? Do they preferentially charge when the off-peak pricing starts in Ontario, when electricity gets cheaper? And what we're showing here in particular is how much more are electric vehicles going to increase peak demand. And so this is in the light gray or the light coloring here. If you were to ignore temperature, just having electric vehicles on the grid is going to increase peak demand. But how much more do we get if we think about these extreme days, right? And so yes, fundamentally, if you're modeling electric vehicles and their implications for the grid, just having the vehicle is the bigger chunk. But this temperature effect is really non-trivial. Right, we're talking, to me, one of the most realistic scenarios here is the residential charging, so people charge as soon as they get home, right? So electric vehicles are going to add potentially on the coldest day in January, 1,500 megawatts of demand to the system. For reference, the typical peak demand right now is about 9,000 megawatts. So we're talking a whole new large power plant needed to meet that demand, to meet these, this 1.5 gigawatts. That's basically a large nuclear plant needed to meet that peak. And about a third of that is coming just from the fact that it is the coldest day, just that temperature effect. So if you ignore that temperature effect, you're missing quite a large chunk of what we're doing to the grid. All right. I'm watching the time tick. I actually don't know what time I started, but I suspect it was close to 10 minutes ago. I'm going to skip over a little bit of this and just say, look, we also did the study of the grid itself. For getting electric vehicles, we'd like to merge these two studies soon, but we haven't done that yet. And we said, power generators are going to become less efficient. And demand is going to go up. Both of these things are going to happen as extreme weather increases, and especially in the summer. So what are we seeing here? So here's our time series right now of our effective capacity. This is our ability, the maximum electricity we can supply at any one time. And here's the historical demand curve with no climate change. It's a little bit higher in the summer because it's hotter. But some of the reasons, for example, that you heard from Professor Touchie. We look at the effective capacity in the summer. You don't see major changes, but there are some non-trivial, a couple % changes here where we do get a little bit less capacity because our power plants don't run as efficiently when it's really hot. But more importantly, you see a big increase in the overall system demand. Again, this is without the electric vehicles. This is just, hey, summers are going to get hotter. We have more heating demand. And what you may notice is right in these extremes, on some of these extreme days, we're starting to get some overlap. So let me get rid of some of the noise there. We're starting to get some overlap there where our demand may outstrip our supply. Now, there are lots of simplifications that went into this model. At the end of the day, we are not actually forecasting what the grid will look like in 2040. But what we are saying is, if you don't account for climate change by 2040, which many system operators are not doing, you're going to miss some big demand spikes coming that are going to happen to correspond in particular to times when our supply is the lowest. And so it's not enough just to think about demographic change and to think about historical weather profiles. You better be thinking about what these new extremes might do and what risk there is to possibly not being able to meet our electricity supply at any given hour. All right. So bottom line, climate change, both climate, just climate variability, and climate change influence our energy and transportation systems in ways that are often overlooked. It's going to open up new opportunities for fuels with poor cold weather properties. We're talking a couple % change in our energy use from vehicles, which can be fairly substantial in terms of the impact they could have on the grid. So at 30% electric vehicle penetration, electric vehicles could increase our winter peak electricity demand by 15 to 20%. And a third of this is driven by the cold weather. And if you don't account for climate change, you're going to have a higher risk of loss of load, meaning inability to meet your electricity supply by 2040. All right, so there's lots more to do. This is a very quick whirlwind teaser of some of the things we've been looking at. Really interested to find what other connections there may be for how the existing changing climate is going to change our emissions. And lots of other pieces too, right? As we have to adapt to climate change, what's the embodied emissions in any new infrastructure we have to build, for example, or what kind of changes, what our mitigation efforts, right? As we start to move towards electric vehicles, does that increase or decrease the vulnerability of our energy system, right? So lots and lots of interactions to find. That's what I like doing, thinking about the system scale. I have no idea if I'm over time. I probably was. I'm happy to take questions by email though, or I'll answer them in the chat.
Yeah, thanks, Daniel. There's one question that I'm pretty sure pertains to you in the Q&A chat there. But Marianne.
Yeah, you want me to do that one in writing?
Yeah, do that one in writing, and then we'll just so that we can try to get at least the presentation part done as on time as possible.
Sounds good.
Marianne, it's your turn.
Sounds good. All right, can you all see my screen? Perfect. Well, thanks very much. Thanks, everyone. Thanks, Jamie, for the wonderful organization. I'm going to take you back from Daniel's national view to people, just very, very individual microscopic view of greenhouse gas emissions. Let me see if I can move my slide. So just to contextualize, a lot of the research that I do is anchored in transportation, and a lot of it is anchored in the GHHA. That's our lab, that's our test bed. So just to kind of anchor a little bit traffic related emissions in the TGHA, this is the most recent inventory that we have that my team has done for 2016, because that's when we have the most detailed data. If you look at the generation of greenhouse gas emissions, the whole region from transportation, from moving people and goods, is generating about 35,000 tons in CO2 equivalent per day. Most of it are coming from cars and SUVs on the road. But if you look at traffic-related air pollutants like black carbons, which also has a global warming potential, but we're more concerned about the health effects of black carbon, or nitrogen oxides, we're going to see a much larger share for truck movements, commercial vehicle movements. And this is really going to sort of, anchor a lot of the trade-offs in terms of, well, what kind of policies are going to help us really achieve deep reductions in greenhouse gas emissions, but also gains in air pollution and public health spread across the population. Now, what I'm going to talk about today is sort of a study I'm hoping to cover a few studies, but if I don't, and if we want to make gains in with respect to times, I'll stop with at this one study where we recently looked at personal greenhouse gas emissions from transportation. So to do this, we used data from the Transportation Tomorrow survey. So the Transportation Tomorrow survey is this travel survey that is done every 5 years for the region, the whole region, the Greater Toronto and Hamilton area, and where we look at a representative sample of the population. We collect data about what people do in a day, all the things they do. I walk to the bus stop, I ride the bus, I go to work, I stop, pick up my kids from daycare, I go to the gym. So we have, complete travel diaries for individuals as well as socioeconomic characteristics. And you know what? I just realized that I don't have this full screen mode. This is better. And their socioeconomic characteristics. And so with this, what we basically did is we took every single trip in the survey. So we have about 160,000 individuals, close to 500,000 trips. And we tracked all the movements that people are doing. I'm not going to focus on methods at all in this entire presentation. Just believe me that we quantified the emissions from all the different modes. And this results from, various previous pieces of research where we have generated, very robust emission inventories for different modes. If you look at just the distribution of how people move in the region, not their emissions, you're going to see about 63%, the biggest chunks of people actually drive. And we have 13% people who are passengers in cars. So they're not driving, but they are with somebody who's driving. We've got transit in gray, which is about 11%. This is subways, streetcars, buses, go buses. We usually put GO rail in a different category because, trains are diesel fueled and they have very different emission factors. And we have about, the yellow is walking. So about 6.6% of the trips are actually done by walking. That's not people, that's just trips. If you go to people, you might get a slightly higher share. And then cycling also, but they're really small shares. And so what we did is we said, let's estimate the total greenhouse gas emission from all these people. And we've estimated it's about 25,000 tons per day from all these people. Slightly different than the 35,000, right? Because this is not including commercial vehicle movements or business travels or UPS trucks, distributing things. And then we said, let's take all these daily greenhouse gas emissions and bring them back to where you live in the GTHA, and let's look at what they look like, what the map looks like. And needless to say, kind of confirms our intuitive hypothesis, right? If you live in the suburbs, if you live far from the city center, you are going to generate in a day to fulfill your transportation needs a much higher amount of greenhouse gas emissions than if you live in the city core or very, very close to where you work. So confirming, very intuitive hypotheses, but it's just nice to have the numbers to show that. So then we said, let's actually look at those individual level GHG emissions and see how they're distributed across the population. And so this is kind of a Lorentz curve. So what this is showing you is what percentage of the population is contributing to the percentage total greenhouse gas emissions. And the orange line is the one-to-one line. So very interesting here. You can clearly see if I focus on the 0.7 number on the x-axis, which corresponds to 0.3 on the y-axis, this pretty much tells you that the highest 30% of the population is emitting 70% of the emissions, right? So we have 30% of the population responsible for 70% of the emissions, and we have 70%, the entire 70% remaining of the population that are only generating 30% of the emissions. So there's definitely a lot of inequality in terms of who's generating transportation-related greenhouse gas emissions and who is not. So we started then diving into these questions of inequity and disparity. So we dug into census data and we started looking at, emissions, personal emissions, as a function of different variables. The first one you always think about is income. So what you see here on the x-axis is different categories of greenhouse gas emissions in kilograms per person per day. And on the y-axis, there's a median income, right? And there's certainly here a trend. It's mild, but it's definitely there that individuals with higher income are actually in the higher emission category. To contextualize things for you, so like a typical car emits about 200 grams of CO2 per kilometer. Okay, so if you drive 10 kilometers in one way, that's 2 kilograms, and another trip another 10 kilometers the other way, that's 4 kilograms. So if you're emitting like 8 to 10 kilograms a day, you're driving a lot on a daily basis, right? But this includes everyone. This includes people who take transit, right? So if you take transit, the emission intensity for transit in the GHGA is about 18 grams per kilometer, right? So even if you travel a lot, your footprint is much lower. We also looked at here, so this gives you also another idea of this inequality. This is called the disparity ratio. So it's very simple. What we're doing is we're looking at the emission intensity of across different income groups, and we're dividing it by the emission intensity of the highest group, right? To give you an idea of what is the proportion of the emissions that are borne by every group. This is not total emissions. This is greenhouse gas emitted per kilometer, right? So this is sort of like your intensity. If you normalize for all the trips that you do, if you're a lower income individual, you have a lower emission intensity, which means more likely you are taking transit, you are taking the bus, you are not driving. And in the highest income category, you're going to see, the highest emission intensities. So beyond income disparity, we thought, okay, well, income is personal. You have a higher income, chances are you have more cars, you drive more. But also let's look at the land use. Let's look at, the built environment and where you live and where you choose to live. And so we use a measure in transportation that's called accessibility. And we use a very simple measure of accessibility, which we call the cumulative opportunities measure. What we do is very simply, for every neighborhood, we go and we generate a buffer of 3 kilometers or 2 kilometers or 10 kilometers, and we count all the different opportunities, jobs, restaurants, commercial establishments, community centers, parks, whatever it is, you name it, all these opportunities that are accessible to you. And so you can generate usually accessibility measures by mode of transportation for specific, sectors, for specific opportunities. What we wanted to do is actually look at how these measures of accessibility relate with the greenhouse gas emissions, right? And so what this is here, this is sorted in quintiles of accessibility. And what you're basically seeing is that neighborhoods that have the highest levels of accessibility have actually the lowest greenhouse gas emissions per capita per person, right? So if you live in a neighborhood that has higher population density, more commercial establishments, you are more likely to be, walking or biking, and therefore your transportation carbon footprint is lower than that. We looked at average number of vehicles. So keeping everything, everything else is as it is. If you have more cars as a person in your household, you are emitting more, right? And then that again confirms our intuitive hypothesis. We didn't see a very big effect in terms of the total number of trips. You see a very mild effect here in terms of, so people who do a lot of trips in a day are not necessarily the ones who are emitting more. It's really how you're doing your trip, right? And so, and that's actually an interesting finding to us, because I've always thought that, trying to reduce transportation greenhouse gas emissions means we have to try to make people not travel a lot, right? Just, work from home and not have to go around and do a lot of things. But in fact, just on its own, in its own right, doing a lot of trips in a day and chaining all these trips because you're running a lot of errands is not really a big predictor of your total carbon footprint. Is all the other things that we're talking about. It's essentially how you're doing these trips and what modes of transportation you're using. What's quite interesting here is that if you look at this map of greenhouse gas emissions, and this is, spread over the entire GTHA. My team also does a lot of what we call chemical transport models for air quality, right? So we take emissions and we disperse them and we look at atmospheric chemistry. So this is a map of black carbon concentration in the GTHA. If you look at those, right, where in this map, the warmer colors are the highest levels of air pollution. And then in here, you have the lightest colors are the lowest emitters. The first thing that strikes you is that, well, in fact, that, air pollution is actually worse in the areas where people don't emit, right? So people who live in places and who don't contribute too much to emissions are actually exposed to higher levels of air pollution. And those individuals who are living in areas where they generate more emissions are actually enjoying better air pollution. Again, it really confirms our intuitive hypotheses that everyone who's driving is in the city and dumping most of the emissions in the city, where, you know, individuals who are embracing more sustainable modes of transportation are actually breathing these. So we looked at, again, this kind of relationship. So here on the y-axis, you have NO2. So I'm switching here to NO2 exposure. And then on the x-axis, you have these emission categories, right? You actually do see a trend where if you are in the highest emission category, you live in an area that has a much lower level of NO2 than if you are in, you know, the lower emission categories. You're going to see here this blue part, right? And this only emerges. This is the individuals who are living in the city, right? And emitting very little and yet exposed to very high levels, but living in some small pockets of the city. So like, you know, Rosedale, for example, which is, you know, slightly lower ambient concentrations than the rest of the city. So you'll have also these little pockets in the city where you do have people who are embracing and you know, lower you know, modes of lower carbon intensities, and yet, you know, enjoyed slightly better air quality. But this is really, you know, very small anomaly that shows on the maps. So when we put all of this together, we basically looked at all of this information. We said, let's train actually a machine learning model. This is a gradient boost model that would look at, you know, all of these characteristics for every individual and try to predict, like, can we actually predict, you know, your carbon footprint from transportation using information that has nothing to do with, you know, what you are doing right now. So what what this plot shows you is that when a color is red, it means that that feature is increasing. And on the x-axis, you'll see that if the feature is red in the positive, it means it has a positive effect on the outcome, right? So if you look at, for example, the average number of vehicles, you're going to see that as the number of vehicle increasing, so the feature is becoming red, the model output, the total carbon footprint from that individual is also increasing, right? So that also helps to visualize whether some relationships are monotonic, like very linear, or some of them are not, like U-shaped, for example. So it captures, you know, a little bit better the relationship between these. And needless to say, you know, all of these things that I showed you are actually powerful predictors. You know, the average number of vehicles, the total number of trips to a small extent, the accessibility, the income, population density, the percentage of visible minority also is there. It's a very, very, very small effect. And so that's why, you know, it actually made it into the model, but it's a very small effect. We found much bigger effect just using income in its own right. And what we're branching into right now is this idea that, so now that we've quantified those personal greenhouse gas emissions and we have them, you know, mapped out for different parts for the entire city, and we're using all these characteristics from the travel survey to predict greenhouse gas emissions, we thought, well, if I take a picture, like an aerial view of the neighborhood where you live, it already embeds everything that I need to know about that neighborhood. If you have curvilinear roads, if it's suburban, if it's urban, it probably how many cars are in it. So why don't we actually start training deep learning models that just use the image? So take a look, take an image and predict your carbon footprint from transportation. This is kind of the big thing that we've embarked upon. We have 250,000 images for the GTHA that we're training using convolutional neural networks to see if we can actually just predict GHG emissions from the images. This is just only for transportation. And with this, I think I'm going to try and close the gap, and I'm not going to go through the other studies that I wanted to talk about and stop here so we can move on. Is that fine, Jamie? All right.
Yes.
Oh, sorry.
All right. Thank you, Marianne. I do see there's a few questions in the Q&A tab if you want to pop over to those. And now it's time for Paul and Karen to to give their insights into the collaborative work that we have been doing here. And then we'll have a few minutes for Q&A after that.
Great, thanks, Jamie. So in the interest of time, I'm going to probably keep it a little bit on the short side, but hopefully, after these presentations that you've seen, you see that there's a lot of interesting research going on. But I wanted to emphasize one of the things that we as a group had to kind of overcome at the outset of our formation is really, a discontinuity between the type of information that climate models can provide, for example, and the type of information that engineers need in order to run like wind models or structural models or building design and all these types of things. And so filling that gap with education and training has been a really big part of the collaborative effort between engineering and climate science. So I'm just going to talk a little bit about that side of our involvement, our being Paul and my involvement with CSE. So of course, there's been sort of education between us, sort of learning from each other has been a big part. But we've also embarked, as Oya mentioned, into various educational projects. So we've been developing master's courses for engineering, and as well, last year we ran a series of workshops that have now been we're converting into a set of eCampus Ontario modules that with the aim of helping other engineering faculties and departments across Ontario to bridge this gap that we've been have some sort of hands-on experience kind of working through together. A few other projects, as Oya mentioned, was the deep 1 week course for high school students that we ran in the summer. And again, this is kind of starting to get potential prospective engineers, students who are maybe coming into U of T or other institutions thinking about doing engineering, to start even already thinking about the interface between climate science and engineering. So that's been kind of a big part. And so in terms of research projects, I think that's been sort of where I've been contributing as well, is kind of being at that kind of translation, playing that translation type of role between what climate science and climate models can provide in terms of useful information for engineering projects. So maybe I'll pass it over to Paul, who can sort of fill in a little bit more about the specifics of what's going on for these research projects.
Yeah, thanks, Karen. And I think that the education process for all of us has been, one of the most valuable things for me, and seeing this kind of generation of students all kind of interacting with us at different levels. And I guess there's just a couple of points to make that working through this center here has, made me really aware of how much actionable climate science information there already is out there. We talk a lot about the need for translation, and as we dug into these projects, even for present day conditions, there's a tremendous amount for me to learn as coming from the climate science background, and also to just understand current engineering practice. So this came up in the Lifecycle analysis, in the wind engineering analysis, that a lot of what is currently done is worth thinking about, current engineering practice, and also just the current way we train our own students in climate science to be aware of some of these issues and problems. And the second thing I learned really is the need to go into detail. We really have to figure out how the practice works. So especially when we're talking about extreme conditions, extreme wind loads, understanding what is meant within engineering for design wins, and all the design criteria that go into engineering. This really requires deep expertise, which we have to gain through communication. So this has been very, very important. And then when we get to the opportunity of having all that information shared, actually going towards new design or new ways of doing things, this is where it gets really exciting. So Daniel mentioned this idea of redesigning supply orbits, for example, for biodiesel according to weather conditions. I mean, I'm hoping that with this kind of information, we're actually bringing, and that's even under present day conditions, and also into the future, that this can have some really positive influence. So it seems like there are existing gaps in weather and climate science. Climate change is happening now. We've already had about a degree or so of warming, and so we should be adapting to the climate change that's happened now. And it's fairly, I mean, it's not a happy story, but I think what I'm seeing here is a lot of potential for continued interaction between these communities, and maybe getting some of our students who come in more from the physical science side interested in these problems, and able to better go out and engage in collaborations of their own. Just if I could just say one more thing, and that is that in the area of climate modeling, where I guess a couple of you, both Oya and Daniel, mentioned that I would be talking about downscaling, I would just say that here, is an area where there's a lot of opportunity to advance the rate at which climate modeling information gets translated and actually transformed into useful information in engineering practice. And I think it's a real challenge, because actually getting the data into the right kind of sampling and technical formats remains a challenge, especially as the volumes of data become practically overwhelming. And so I think that's a technical challenge for the future, and something we've had to deal with a little bit ourselves. But that's something I'd really like to see going forward, is more attention on that. And that's all I want to say now, because we have so little time left for the open discussion, that maybe it would be best to sort of open it up to any further questions.